Hello everyone, this is Professor Hu. In this lecture, I will introduce some very basic concepts related with programming. This is the second part, computer science. Now I will discuss the second topic, computer science. What is computer science? Computer science is a study of algorithms. So we will discuss the fundamentals of algorithm. What is computer science? Computer science is the study of algorithms, including their formal and mathematical properties, their hardware realizations, their linguistic realizations, and their applications. What is an algorithm? An algorithm is a set of operations that are well ordered, unambiguous, or effectively computable, producing a result and to hold in a finite amount of time. Here, well-ordered means steps in an algorithm are not exchangeable. Upon completion of an operation, we know which operation is to do next. Unambiguous and effectively computable means every operation in an algorithm must be doable or executable without any ambiguity. For example, instruction start over is ambiguous. It does not clearly tell where to start over. But start from step 3 is unambiguous. Producing a result means an algorithm must produce a result that is observable to a user, such as a numerical answer, a new object, or a change in the environment. To halt in a finite amount of time means an algorithm must stop by itself in a finite amount of time. No algorithm should run forever. If that happens, there must be a mistake in the algorithm. These are the properties of an algorithm. Hardware realization will affect algorithms because hardware speed will determine if an algorithm is realistic to run on a computer hardware. Computer hardware based on architectures such as von Neumann machine and illustrated by Turing machine. Algorithms can also be implemented based on network communications. Algorithm implementation is also based on linguistic realizations because the language must support implementation of algorithms. So about linguistic realization, we'll discuss language categories, language levels, language elements, and language grammars. There are many computer languages. There are computer languages for general programming, web page design, database query, data analysis, and for many other uses. For general programming languages, there are C, C++, C#, Java, Python, and so on. There are basically two types of general programming language, compiled and interpreted. Compiled programming languages require the whole program to be converted to machine code, and then the machine can execute the entire program. Where interpreted programming languages does not require to convert the whole program, but just convert one instruction in the program, executed, and then the next one converted to machine code and then executed, and so on. Compiled programming languages include C, C++, C#, and Java. Interpreted programming languages like Python. Web page design languages include HTML, JavaScript, and Python. Database query languages like SQL, and languages for data analysis such as R and Python. According to where a computer language is oriented, it belongs to machine language, assembly language, or high-level language. A machine language consists of a set of machine-oriented instructions that are implemented in computer hardware wires. The implementation can be either a complex instruction set or a reduced instruction set. Complex instruction set computers try to implement more complex instructions to help to program, while reduced instruction set computers try to implement a small set of instructions so that the hardware implementation is easier. An assembly language consists of a set of mnemonics of machine language instructions. So it is a machine-oriented and low-level language. Assembly language instructions must be converted or say assembled into machine instructions before they can be executed by its computer. A high-level language consists of a set of reserved keywords, extended libraries of predefined functions and classes, and a set of grammar. High-level languages are human-oriented, so they are of high level. High-level languages use mathematics notations and are close to natural languages, such as English. High-level language instructions must be converted to a machine language before they can be executed by a computer. There are two methods in conversion. Compiling is converting a whole program to machine code. Then the converted program can be executed. Interpreting is converting and executing a single instruction, then the next instruction. High-level languages provide easiness and flexibility in programming. They are not bound to any specific machine. Similar to a natural language, a high-level programming language consists of elements, data, punctuation, operators, expressions, statements, and some reserved keywords. There are three types of data: labels, variables, and constants. Labels are values in the instructions that can be directly used, not stored in memory. There can be many kind of labels, just the available data types of the computer, such as integer, float, and characters. Like number 2 is a label value, real number 3.7 is a label value, character A is a label value. Second type of data is variable. A variable is a data stored in memory that can be updated during execution. For example, int x declare a variable x. X is an integer, so it uses the space that can hold an integer in the memory. To declare a variable is to declare an amount of space in memory. The third type of data is constants. Constants are data stored in memory that cannot be updated during execution. So you can think of constant as a kind of a spatial variable. For example, declare constant pi equal to 3 0.14. When we declare the constant pi with a given value, and the value is stored in the memory, and the value there cannot be changed in the program execution. Another element is punctuation in the programming language. Punctuations are used to organize data and format the program. For example, we use curved brackets, round brackets to organize the blocks in programming code. And another kind of element is operators. Operators are used to work on data to perform some operations, such as addition, subtraction, multiplication, division, and modulus. And yet another type is expressions. Expressions are data variable constants or their combinations connected by operators, or other expressions that are connected by operators, like phrases in natural language. For example, number 2 is an expression. 2 plus 3 is an expression. Variable x divided by variable y is an expression. Constant pi multiply variable r power 2 is an expression. So basically, expressions is kind of formula we used in mathematics. But there can have other expressions like some strings. Now another element in programming language is statement. Statement is like a sentence in a natural language. A statement performs a single piece of task. For example, x equal to x plus 1, semicolon. This is a statement, is a single complete statement that can complete a single task. Here the task is to increment x. Now another kind of elements in your programming language is reserved keywords. Reserved keywords are used to define data, statements, control structures, and blocks such as functions and classes. For example, int is used to declare integer. Float is used to declare float numbers. If and else are used to declare or define a block of conditional statements. So these are the basic elements of a programming language should have. Also similar to a natural language, a programming language has a set of grammar that consists of syntax, semantics, and pragmatics. Syntax is about how characters combine to form a program. Semantics is about what the expressions, statements, and entire program mean. Pragmatics include common programming idioms, programming environments, standard libraries, and ecosystems. Algorithms are used to implement software, including system software and applications. Today, computer applications are almost everywhere, have been used in all industries. Now let me discuss fundamentals of algorithms. In this section, I will discuss 3 basic control structures used in algorithms, tools used in designing algorithms, data types and data structures used in algorithms, and some basic algorithms. No matter how complex an algorithm is, we may use just three very basic control structures to design it. The three basic control structures or fundamental control structures are sequential, conditional, and iterative. All general programming languages support the three basic control structures. The sequential or sequence control structure is essentially implemented by the computer hardware. Thus, the instructions are executed one after another. Therefore, this is the default control structure in your program. The left figure shows an example of a sequential control structure. It is executed step by step from start in the top down through all the steps to the bottom. Like x equal to 1, then print x, then x equal to x plus 1, then print x, then x equal to x plus 1, then print, and so on until the end in the bottom. The conditional, or say the decision or decisive control structure, executes one of the multiple branches depending on whether the condition is true or false. The left figure shows an example of a conditional control structure. It first checks the condition. Is the score above 60? Then, if yes or true, it executes print pass. Then it executes the next available instruction. If no or false, it executes print fail. Then it executes the next available instruction. The iterative, or say the repetitive or loop control structure, executes a block of statements multiple times until a specified condition is met. The iterative control structure is useful when one or more actions are to be done more than one time. The left figure shows an example of an iterative control structure. It checks the condition, is x smaller than 5? If yes or true, then it executes the loop body, which consists of display, are we having fun? Then increment x, then check the condition again, x smaller than 5? If no or false, it executes the next available instruction below. There are two types of iterative control structures. One is pre-test, another is post-test. In pre-test, the condition is tested before each iteration of the loop body. In post-test, condition is tested after each iteration of the loop body. There is at least one iteration that occurs in post-test iteration. Now we discuss the tools used in designing algorithms. We only discussed the two most popularly used tools, flowchart and pseudocode, that are used in designing algorithms. Flowchart consists of a set of symbols you can use to design an algorithm. However, only a few listed in the right table are essential. Look at the table. The first symbol is an oval. An oval indicates the start or the end of an algorithm. Second symbol is rectangle. This indicates a step or a process in an algorithm. The third is a parallelogram, which indicates an action by the user. The fourth is a diamond, which indicates a decision. And the fifth is an arrow, which shows the program flow. Please refer back to the three basic control structures we just discussed for the flowchart used there. Another very popularly used tool in designing algorithm is pseudocode. Pseudocode is a plain English language description of the steps in an algorithm or a system. For concision, pseudocode often uses structural conventions of a normal programming language and uses compact mathematical notations. Pseudocode is for human reading rather than for machine reading. For example 1, an example of sequential control structure. We just list the steps using pseudocode. And in the pseudocode, we use the kind of mathematical notations like x equal to 1, x equal to x plus 1. So these are kind of mathematical notations. And the sequential control structure just shows the algorithm listed in some steps. The step-by-step list shows the sequential control structure. It's actually natural sequence executed by the computer because sequential control structure is actually implemented by the computer hardware. The second example is an example of a conditional control structure. We use if-else to build the conditional control structure. If score is larger than 60, if this is true, then print pass. Else, print fail. The third example is an example of iterative control structure. First, set initial value x equal to 0. Then use a while to form an iterative control structure. The condition x smaller than 5 will control to enter the loop or not. While x is smaller than 5, do the loop body. The loop body consists of two statements in the example. First, display, are we having fun? Then increment x. It will go back to check the condition. If the x is smaller than 5, it will do the loop body again. Otherwise, it will leave the loop body to execute the statement below. Why pseudocode? Natural language is expressive and easy to use, but is verbose, unstructured, and ambiguous. Programming languages are structured and designed for computers, contains fuzzy and cryptic grammars, and hard for people to understand. Well, pseudocode lies between natural language and programming languages, and it's probably better than natural language and better than programming languages. So, pseudocode is popularly used for algorithm designing. Let's use an example to show how an algorithm can be represented by pseudocode and flowchart. Suppose we have a task to calculate average miles driven per gallon. If it is greater than 25 miles per gallon, display you get good gas mileage. Otherwise, display you can improve. The left side is an example of pseudocode. The pseudocode consists of 8 steps. First, get values for gallons used, starting mileage and ending mileage. Then, calculate distance driven equal to ending mileage subtract starting mileage. And then calculate average miles per gallon equal to distance driven divided by gallons used. And then print the value of average miles per gallon. And then there's a conditional structure. If average miles per gallon is larger than 25 miles per gallon, then print you get good gas mileage. Else, print you can improve. And finally, stop. It is good habit to use start for an algorithm in the beginning and stop in the end of the algorithm. Now for the same algorithm, at the right side, we use an oval to indicate the start of an algorithm. Now the first step, get gallons used, starting mileage and ending mileage. We use a parallelogram indicate an action. Here need to accept input from the user. Then calculate distance equal to ending mileage subtract starting mileage. This is a process. Use rectangle to represent. And then calculate average miles per gallon equal to distance driven divided by gallons used. And this is also a step process in the algorithm. Use rectangle to represent. And then the condition. Compare average miles per gallon larger than 25. If it is yes, we go to the yes branch, print you get good gas mileage, and then stop. If the average miles per gallon is not larger than 25, then execute the no branch, the right branch, print you can improve, and then stop. Stop is to finish the algorithm. So you can compare the algorithm represented in the pseudocode and in the flowchart, and think of them and how you can write your algorithm using pseudocode and flowchart to represent your algorithm. Now let's discuss data types and data structures in algorithms. Algorithms are essentially processing data. The different types of data use a different amount of memory space. Data can be organized together to form various data structures. Well-organized data structures help design more efficient algorithms. Different languages support different data types. The following data types are generally supported by most programming languages or most all programming languages. Integer is of any integer, like number 1, 34, and 85. Real can be any real number, like 79.23. Boolean data type will get values of either true or false. Char means any character, like small a, big E, number 1, pound sign, question mark. A character should be enclosed in a pair of single quotes. Different languages support different data structures. The following data structures are generally supported by most programming languages, like array, linked list, stack, queue, etc. An array is a structure of fixed size which can hold items of the same data type. Most programming languages provide predefined functions to operate on arrays, such as traverse, search, and update. Every element in an array has an index or subscription, indicating its position in the array. Array index starts from 0. For example, the red array has A0, A1, and A2, and they equal to 1, 2, 3, respectively. The usages of array can be used to build other data structures such as lists, heaps, hash tables, vectors, and matrices, and can be used for different sorting algorithms such as insertion sort, quick sort, bubble sort, and merge sort. A linked list is a sequential structure that consists of items in linear order which are linked to each other. Elements in a linked list are known as nodes. Each node contains a key and a pointer to its successor node, known as next. The first node is the head, and the last node is the tail of the linked list. Linked lists can be used for symbol table management in compiler design and can be used in switching between programs. A stack is a LIFE structure. LIFE means last in, first out. The element placed at last can be accessed at first. The operations on stack are called push and pop. Push is to insert an element onto the top of the stack. Pop is to delete the topmost element and use it. Stacks can be used for expression evaluation, and can be used to implement function calls in recursive algorithms. Data structure Q is similar to a stack, but a queue is a FIFO structure. FIFO means first in, first out. The element placed at first can be accessed at first. Queues operations are called in-queue and dequeue. In-queue is to insert an element to the end of the queue. Dequeue is to delete the element from the beginning of the queue. Queues can be used to manage threads in multi-threading programming, and can be used to implement queuing systems like priority queues. Okay, now we are going to discuss a few very basic algorithms. Besides designing an algorithm as a solution to a problem, we need to evaluate the efficiency of the algorithm so that we may compare between different algorithms as solutions to a problem. The study of the efficiency of algorithms is called the analysis of algorithms. Algorithm efficiency is mostly focused on time complexity and space complexity. Time complexity is describing time spent in executing an algorithm, and space complexity is describing memory space used in executing an algorithm. The less time spent, the better, and the less space used, the better. We will discuss searching and sorting as examples of basic algorithms. The searching algorithms are used to search and find one or multiple elements in a set of data. We will briefly go over the following simple search algorithms: sequential search or linear search, and before discussing searching, let's have a problem for searching. Given a value n that is larger than or equal to 1, and a list containing exactly n unique numbers, find and print out a given number in that list. Sequential search compares the given value, 37 is in this example, with each of the values in the list until the given value is found or until all values have been compared. Now we represent this sequential search in pseudocode. The left side lists the pseudocode. First, we set up the values n, that is the size of the list, and then get the values for all the numbers in the list, a1, a2 up to an, and then set the value a, that is the value to search in the list, and set up the flag found to no, and then point to the first position in the list. So we set up I to 0, that is the position, I is the position in the list. And then in a while loop, we will compare the current position I with the total number of the list n. If we have not compared all values yet, we will do the while loop. And inside the while loop, we will see if the value is found. Compare the value in the list with the targeted value A. If found, we set up found to yes, and go to step 8, go out of the loop. Otherwise, we increment the position I, and then come back to compare if I reach the value n. If not, we continue to compare with the targeted value a until we either find the value in the list or not find but have compared all the values in the list. We go to step 8 out of the loop. And then we can see if the flag found is no or yes. When it's no, print not found. Otherwise, print found and stop the algorithm. Now we consider the efficiency of sequential search. Time complexity and space complexity. For time complexity, we look for the best case, worst case, and average case. The best case is we find the target as the first element. We use big O notation to mark it. So we mark it as big O 1. That means just one step found it. And the worst case is we searched all the elements, compared all the elements in the list. We either found it or not found it, but we compared n values in the list. So we use big O n to represent the worst case. The average case is when each value is equally searched. The work will be done varied from 1 to n. So average will be half n, and we use big O half n to represent it. But in complexity, we omit the coefficients. So the time complexity is big O n. And generally, considering complexity, we use the worst case to the complexity of the worst case to represent the complexity of the algorithm. Big O n means order of magnitude n. Now space complexity. There is no extra space used for searching, so space complexity is big O 0. Binary search works on a pre-sorted list of data. It compares the given value, 37 in this example, to the middle value in the list. If the given value is smaller than the middle value, it compares the middle value of the smaller half of the list. Otherwise, it compares the given value with the larger half of the list. It will repeat the comparison until the given value is found. Similarly, we represent the binary search algorithm in pseudocode. Step 1, start. Step 2, get the size of the list n. Step 3, get a sorted array A0, A1, up to an-1. Please note, an array always have index or subscription from 0. The total number is n, so the biggest index is n-1. Step 4, get the value to be searched, A. Step 5, initialize the flag found to no. Step 6, set lower bound to 0, upper bound to n. Step 7, while found is no, do the loop body. Inside the loop body, If upper bound is smaller than lower bound, break out the loop and go to step 8. Otherwise, else. Inside else branch, set midpoint equal to lower bound plus upper bound minus lower bound divided by 2, that is half of the distance between upper bound and lower bound, plus 2 lower bound. Then, if A, that is a midpoint, A midpoint, that is the value in the middle of the array, is smaller than A, then set the lower bound to midpoint plus 1. Otherwise, else if A midpoint is larger than A, set upper bound equal to midpoint minus 1. Otherwise, set flag found to yes. And then it will go back, compare found is no or not. So we can see inside the while loop body, there is a chance to set found to yes. So when found is yes, we will move to the next step, step 8. Step 8, if flag found is no, print not found. Else print found. And then step 9, stop. Now consider time complexity. The base case for binary search is to find the target at the middle point element. We use O1 to represent it because we found it immediately. And the worst case is searching k times, where n equal to 2 power k. And k equal to log n. The average case will be searching half k. Since we ignore coefficients, so the searching time is also log n, or we can use big O log n represent the time complexity of binary search. About the space complexity, we just need 2 variables, lower bound and upper bound, to keep track of the range of elements that are to be checked. So space complexity is O2 or O1. For any constant, we use O1 to represent. Now we discuss sort algorithms. The sorting algorithms are used to put elements of a list into an order, ascending or descending. Efficient sorting is important for optimizing the efficiency of other algorithms, such as binary search, that require input data to be sorted. There are many sorting algorithms. We will discuss the simple sorts as examples: insertion sort and selection sort. Insertion sort picks up each element in the original unsorted list and inserts it into the correct position in the partially sorted list until complete all elements. For insertion sort, we also use pseudocode to represent it. We also first get the size of the list and then value for the elements in the array, and set up the initial value to 1, and then we compare the position with the total number of the list And if it's smaller than the total number, we enter the while loop. And inside the while loop, we will compare the two elements and determine to switch or not until we complete all the elements in the list. And so finally, after we complete the loop, we will have sorted all the elements in the list. About time complexity, we also consider base case, worst case, and then average case. For base case, we compared all the elements, so the complexity is big O n. And for the simplest worst case, that is the array is sorted in reverse order. So we have to reverse every element. And comparing a time and reverse n values so that the complexity will be big O n power 2. And for the average case, it's somewhat between the base case and the worst case. So the complexity is O n power 2. About space complexity. Space complexity is big O1 because we only use one space for the picked element in the comparison. Selection sort is an in-place comparison sorting algorithm. The list is divided into two sections as shown in the animation. The sorted section marked as yellow and unsorted is the original section. The minimum value or the maximum value, depending on descending or ascending result expected, is picked from the unsorted section and placed into the sorted section. This thing is repeated until all items have been sorted. Similarly, for selection sort, we also use pseudocode to represent it. And we first set up the size of the list n, and they get a value for all the elements in the array. And then in a loop, we compare from the first one to the last one. And inside the loop, we will compare the value with the target value, compare the elements and determine a switch or not. And so after the loop, and we will have sorted the elements, and then we can finish that. About time complexity, we also consider base case, worst case, and average case. And for selection sort, all of them are big O n power 2 because we need to compare every element and then sort every element. So it's n multiply n is n power 2. For space complexity, it is big O1 because we only use one space for the picked element in the sorting. To summarize, in this part, I briefly went over the concept of computer science. Computer science is the study of algorithms. So I went over the basic concepts about algorithms. An algorithm is a set of operations that are well ordered, ambiguous, producing a result and to halt in a finite amount of time. An algorithm constructions are based on three basic control structures: sequential, conditional, and iterative. We may use pseudocode and flowchart to design algorithms. We do the analysis of algorithms to find and compare algorithm efficiency based on their time complexity and space complexity. Search and sort are two very basic algorithms. Understanding data types and data structures help us design efficient algorithms. Although almost all computer languages support using the three basic control structures to construct algorithms. Computer languages can be categorized for general programming and specific use in web page design, database query, database analysis, etc. General programming languages can be either compiled or interpreted. These are about the points we covered in this part. Thanks for watching.